So in 3.2, we are going to talk about domain and range. Domain and range is a concept that you probably started in your Algebra 2 class, but you will not do it as extensively, or you didn't do it as extensively as we're going to do it now. Usually in your Algebra 2 course, you might have talked about domain a little bit more than range. We're going to focus on both to prepare you for any higher level maths you might take. So interval notation, we have already talked about. Okay. So I'm going to leave this here for a little bit and let's just talk about it. On this particular document, they have shown the parenthesis as an open circle and a bracket for the closed, and they actually put it on the graph, and that's not necessarily a bad idea, and they as a visual, okay? So these ones here, you'll notice, have an infinity or a negative infinity, and you might notice that the interval matches the direction of the number line, and that's one thing I noticed on the test. There were some of you that were not necessarily putting in number line order. So please make sure that you're always putting it in number line order. So I'm going to leave this up here for a second, and then you can go ahead and, work that through, write that all down, and then we'll talk about it a little bit more. Now, the reason this is in this section, okay, positive infinity is only if you have the tail going to the right. Negative infinity is only if you have a tail going to the left. So you'll notice the ones that have the equal to in them, or it says including, they have brackets on the correct one that you're including. Anytime you have an equal to, put a bracket. If you don't have an equal to, or if you have an open circle, put a parenthesis. And it has to be follow number line order. Because on the interval notation, the left value is your leftmost point, the right value is your rightmost point. So if they're not in the right order, you're not following the number line. You're not giving me a subset of the real number line. So follow the number line. Yes. Okay. Oh, sure, yeah. There's a lot there to write for sure. Everybody good now? No problem. I know there's a lot. Are we good now? Okay. So the sheet that we just copied all that down works if we have a subset of the reals. So like every real number between 1 and 2. So we're including 1.1, 1.0001, 1.7, 1.9, all the way up to 2. So that's all that set of all those decimals and everything between there. If we have a set of ordered pairs, so we call that a finite set of values, the domain and range can be written a very distinct way. Remember, we had said, I think in 3.1, that the domain were the set of x's, the range are the set of y's. So if you want to list out the domain, you're just going to list out, and try to do it in order if you can, because then it's easier to keep track of things, but it doesn't have to be in order. You're going to list out the set of the x's that you used. I used 2, 3, 4, 5, 6. The range are the set of y's that I use. If there is a repeat, this is just, hey, this is what I used. It's not telling you how you used it. So if there's a repeat, I don't care. I'm just going to write what set of y's I used. I used a 10, a 20, a 30, and a 40. I'm not concerned about the fact that I used the 10 twice. That is not what it asks. The domain and range are what x's did you use. It's helpful to put them in least to greatest order. It isn't necessary when it's a finite set like this. Don't use the same R you use for real numbers. The real number R, remember I have that one with kind of like the double back, or some people it says it looks like a T is attached to it. Use just a capital R for range, capital D for domain. Now, it's a lot different if we are finding the domain and range of a function that's just given as an algebraic expression. If I want to find the domain of x squared minus 1, the thing that should go through your head is, what x's am I allowed to use? Are there any x's that I can't use? Like if I can't use 2, maybe I can't use 0. Can I use negatives? Sure. Can I plug in 0? Yeah. Can I plug in 7? Yeah. Can I plug in a decimal, 1.2? Can I plug in 4.6? You can plug in whatever the heck you want, right? So the domain are the x's that you can plug in that don't hurt it, that just give us a value out. The domain of this function is all real numbers. Now, if we look on a graph, so if we were to pull up Desmos, well, I know what the graph of this one looks like, so just let me pretend I pulled up Desmos. I pulled up Desmos, and my graph looks like this. On a graph, the x's appear left to right. So you can see that this graph would go to negative infinity eventually and to positive infinity. And I never have to lift up my pencil or pen. And so you can see that the domain includes every real number eventually. Now, for our purposes, the range, I know they didn't ask for the range at this point, but I want to talk about range. The range, so the domain, I always think of left to right. The range, I always think of bottom to top. This graph has a distinct minimum value, a distinct bottom at -1. And it is a value that I could get if I plug in 0. And then the top of this graph, it keeps going forever and ever and ever and ever and up. So the top of that graph goes to negative infinity. So when looking at a graph, you're going to use interval notation most of the time. In this case, x squared minus 1 has any x I want I can plug in. The graph also stretches from left to right as far as I want. But the range is kind of more restricted. Now let's take a look at part B. Again, there is nothing that messes this up. I can plug in whatever the heck I want. This time, I know approximately what the graph looks like, but in my head I don't. Let's actually go ahead and put it into Desmos. So if you type in 5 minus x plus x cubed, this is what our function looks like. I'm going to draw a little kind of depiction of it here. It looks something like that. So what's the domain? Well, this graph is going to keep extending outward forever and ever and ever. That's where this comes from if you look at the graph. The leftmost side is negative infinity. The rightmost side is a positive infinity. And I never have to lift my pencil. The range, what's the bottom of the graph? How far down can that one go? Yeah, negative infinity, as far as we want to go down. How high up can it go? Positive infinity. So this is kind of an interesting one, that the range is also negative infinity to positive infinity. For now, the ranges we have to get from the graph. There's no other way to get range. The domain, you can use some logical thinking. What can I plug in? Maybe sometimes it's almost nicer to think the opposite way. What can't I plug in? What wouldn't work? Well, everything works on those. The reason they work is because they are polynomials. The domain of polynomials are always negative infinity to positive infinity, or all real numbers. Every real number will work. I can plug in whatever the heck I want. I never have to think about it. The domain of a polynomial function is always all real numbers. That graph will always extend forever to the left, forever to the right, and will have no gaps, jumps, holes in between. Polynomials are wonderful. Now, their ranges aren't as wonderful. You would have to have a tool like Desmos in order to find the range. And I wouldn't expect you to know the range without the graph. And if you're not ready for that actual graph, I would provide the graph. Okay? So range is kind of very much graph related. Domain, we should be able to find some information without a graph. Any questions about that so far? Now, if we have a rational function, okay, so these ones are rational. A rational function, you might recall, is when the top of the fraction and the bottom of the fraction are both polynomials. The domains of a rational function are related completely to their denominators. So, let's fill in this bottom part first. The domain of a fractional function, you must find where the denominator equals 0 and remove those values from the set of real numbers. You must find where the denominator equals 0 and remove those from the set of numbers. Every other number will work. That's the only number that won't work. There might be 4 values where you could get a 0 denominator. All 4 have to be removed from the set of real numbers. Every other real number is fine. So it's super important that you discover where the denominator equals 0. In the graphs of these, wherever the denominator equals 0, you will either have an undefined little hole in the graph, or you will have an asymptote in the graph, like we saw in our original reciprocal or rational function. So let's go back up and look at what they've given us. In example 3a, the denominator is 2 minus x. So this is what I want you to do every time you see a fractional function. Write down 2 minus x equals 0 and solve for x. So we're going to solve that for x. Let's just move the x to the other side. It'll make it positive. And we know then that x is not allowed to equal 2. Now let's think on the x number line. If I said graph x does not equal 2, the only thing you would have is an open circle at 2, and you would shade in everything else. The domain is everything I just colored. So it's every number but 2. I want you to get in the habit of writing that in interval notation. So yes, Set notation says the domain is all x's such that x is not 2. This little line is read such that, and these mean the set of. So this is the set of x's such that x is not 2. You are getting ready for, hopefully, future level of math. And calculus, we don't write it like that. We write it in interval notation. So that's what I need you to get ready for. So what I want you to say is that the domain goes from negative infinity, follow the number line left to right. I'm sorry, that should be a parenthesis. The domain starts at negative infinity, stops just before it gets to 2, almost 2, you use a parenthesis. The little union symbol means or. Then I can go on the other side of 2 and keep going. That's what I want. This little section here kind of shows up where there's a gap. That gap could be a hole. That gap could be an asymptote. That gap could be just a section of the graph that's missing. Okay? Let's do part B. First thing you do, set the bottom equal to 0, solve for x. Let's move the 1, make it positive, divide both sides by 2. Put a little slash to remind you that doesn't work. If we were to graph that on the number line, we are going to have an open circle at 1/2, shade everything else. These start to look very much like the same. Our domain goes from negative infinity, gets to 1/2, almost to 1/2 before it jumps over that gap, and then it goes from the other side of 1/2 to infinity. Parenthesis means I'm almost there. That means I don't reach 1/2. It means I'm almost to 1/2. So think I'm almost there. So instead of 0.5, I might be at 0.44449, 0.49999. But I'm never reaching 5. I'm almost to, or 1/2. I'm almost to 1/2, but I'm not there. So for fractional functions, you must find where the denominator equals 0 and remove those points from the set of real numbers. You know, sometimes you have more, so sometimes you might have a few gaps along the way. Okay? We're going to stop at this example, and then we'll continue these notes tomorrow.